What I have set up here is a treatment planning system called Eclipse, and I have a water equivalent phantom, a very large water equivalent phantom, and I have three photon fields set up on this phantom. And what I wanted to do was simulate some isodose lines and go through percent depth dose curves as well as field profiles for open fields. I know that the soft drop lecture talks about wedge fields and wedge isodose lines, but I think it's just a general introduction, and we probably don't need to get that specific yet, since beam modifying devices is going to come in toward the end of class. Right now I have three fields set up, fields 1, 2, and 3. Unfortunately, because of the limited size of my screen, you're not able to see those, but field 1 is going to be 6x, field 2 is going to be 10x, and field 3 is going to be an 18x beam. They're all set to 100 centimeter SSD, and I have them set to deliver roughly 100 monitor units. And then all the doses that you're going to see are going to be in relative doses, and I'm going to shift between the different energies of these beams so I can show you the different characteristics of the percent depth dose curves as well as the profiles. So you can see on the screen I have this yellow outline. Here is my 10 by 10 field size. All my geometries are set down here. So my gantry rotation is 0, collimator rotation, cupped rotation, those are all 0. I have got a 10 X jaw is 10, Y jaw is 10, and my SSD is set to 100. If I turn isodose lines on for my 6X beam, you'll notice some red lines in here. This red line going down the middle is right down the central axis of the beam. That's going to be my percent depth dose profile that I can pull in here. And then you'll notice three red lines, one here right about Dmax for 6X, one here is at 10 centimeters deep, and then one here is at 20 centimeters deep, and each of those corresponds to a different profile at depth that I'll be pulling in and showing you. The isodose lines are in relative percent. In the upper left-hand corner, you see isodoses and then the little parenthesis in percent. So 100 is 100%, meaning it's my prescription. My dose prescription is 100 centigrade times 1 fraction. So, working out the math, 100 equals 100 centigrade, and then so forth down. What the isodose lines represent are basically dots within this three-dimensional volume that have been connected by similar dose levels. So if I were to take a dose point tool here and I can click, and as I drag all around this phantom, I get on the right-hand side of the screen my total dose percentage. And what the isodose line represents is everything of similar percentage is connected by a line. So if I were to trace along the 90% line, we would see that I'd be set at 90% of the dose. Everything inside of that isodose line is higher. So everything inside of the 90% isodose line is higher. You can see I'm at 92.2. Everything outside of that isodose line contour is going to be cooler. So you see I'm at 87.6 and so forth. If I go down past the 80% line, which is orange, I'm at 75.9. So that's how you read these isodose lines. You'll notice that photons penetrate, they penetrate a very long way. So the white is the 30% isodose line. You'll notice that this goes probably 25 centimeters deep in the phantom. And we'll take a look at that on our percent depth dose curve. The 50% isodose line, which is magenta, is the 50% isodose line determines the geometry of the field. So we say that the light field represents the 50% isodose line. It's essentially our field border laterally. So if we were to talk about characteristics of these beams, so I have 6x right now. If I were to take a depth profile, so starting at the phantom surface and then working my way down, this would be called the percent depth dose curve. It describes how the radiation attenuation changes with depth. For percent depth dose setups, which is an SSD setup, the percent depth dose depends on beam energy, field size, depth in the patient, and SSD. My surface dose, you can see, is right around 30%, just shy of it. We have the buildup region, to Dmax. My Dmax point should be right at about 1.5, and then after Dmax I have this fall off region that trails outward. So at 25 centimeters deep in the patient, you can see I'm still getting 30% of the dose. So that's how we read a percent depth dose curve, which corresponds to the isodose line display, which has very discrete levels, and we can change these levels. In the treatment planning system, I can add a few levels in here, and let me add 70, 60, we already have 50, let me put 40 in. Okay, so now you can see I've added these discrete levels for isodose curves. Some centers will use isodose lines to evaluate their plans, some use a color wash to evaluate their plans. But as I work deep down the central axis, the percent depth dose curve is describing how the dose changes with depth. If I were to change beam energy, what you're looking at right now is 6x. If I were to look at 10x, this is what happens. If I were to look at 18x, go back to 10, go to 6. I'm going to jump from 6, where you see Dmax was at 1.5, and I'm going to jump up to 18. You can see my Dmax is right around 3. So I've doubled my Dmax. My depth of maximum dose has gone from 1.5 to 3. My surface dose has decreased. Remember, I was at 28, now I'm at 24, so I have a larger buildup region, but then I also have a smaller fall off. If I equalize 6, 10, and in 18, the purple represents the total dose from all three fields, so we kind of have to ignore that. But if you just look at the three fields down here, 6 is going to be this pink, 10 is going to be this yellow, lime green color, and then cyan is going to be 18. And you can see the three of them each have a separate and distinct Dmax, and that makes sense. If I could zoom in, it's hard to tell right now, but if you could zoom in, you can see that my surface dose decreases as my energy increases. So a general rule is photon beam energy increases, skin dose or surface dose decreases. This is inverse to electrons, which as electron energy increases, surface dose increases. We said that, or I said percent depth dose depends on beam energy. And what that means is that, remember pink we have 6x. My percent depth dose at 6x is smaller than 10x, which is smaller than 18x. So percent depth dose increases based on beam energy. For a given depth, I have more dose at higher beam energies because I get higher penetration, means slower fall off. Let me put my weighting back at 6x only. Take a look at the isodose lines and see what happens. This is 6x, this is 10x, this is 18x. So everything shifts downward. Again, 6, 10, and 18. I'll go back to 6. Next, I want to talk about beam profile. Okay, this is a beam profile at a depth of Dmax. So I took a measurement. My first beam profile up here is at 1.5 centimeters, so Dmax for 6x. Parts of the beam profile, 0 is going to be the central axis. So dose beam profiles are typically normalized, so 100% of the profile is located on the central axis, and everything's relative to that point. We have a slight increase. We have a slight increase as we go out laterally. These are called horns. If there's a shoulder region that rounds, we come to 80% of the dose. 80% of the dose represents the inner portion of the penumbra. You can see my 80% is at negative 4.9. 20% of the dose is the outer region of the penumbra, is at 5.3. So my penumbra, the dosimetrically defined from 80% to 20% isodose line, or the 80 to 20% on this beam profile, goes from 4.9 to 5.3. So you have a 4 millimeter beam penumbra. And then after the penumbra, we come to the tail of the photon beam. So it's very important to note that the light field on the patient represents the 50% isodose line. It doesn't represent 0. So outside of the light field, you have dose that's being delivered to the patient. In fact, I am 1.5 centimeters outside of the light field here, and I still have 3% of the prescription doses being delivered at this point. If I look at my 50% isodose line, you can tell that I'm at -5. If I look at 50% on this side, I'm at +5. So this is what we would call full width half max. So the full width at 50% is 10, which makes sense since I have a 10 by 10 field size. There's a slight magnification since I'm at 1.5 centimeters and the field is defined at 100 centimeters, but you get the gist, is that full width half max describes my field size. And this makes sense since I'm at 50%, 5 centimeters out from the central axis on either side. The horns are caused by the flattening filter, and that's a conversation for a different day, but you can tell as we go deeper in the patient, you can see what happens to the beam profile. So this is going to be a beam profile at 10 centimeter deep. So you can see how the two look different. Here, these distinct horns at 1.5 centimeter deep have gone away. So now at 10 I have a slightly rounded shoulder, a slightly more rounded shoulder. Okay. At 20 centimeters deep, I have an even more rounded shoulder. And the rounding of the shoulder is caused by the flattening filter in the treatment head of the machine. That's what gives rise to the horns at shallow depths and then these rounded shoulders at deeper depths. And that's because of the beam hardening caused by the flattening filter. Let me turn to 18x. And you can see what happens. So 18x kind of homogenizes everything. So we don't have as much of the horns. We have less of the shoulder, and that has to do with the penetration of the beam. So the horns and the rounding of the shoulders and the curves, the profile curves, are caused by beam hardening and absorption effects. Well, those are mitigated or decreased as we increase the energy. So an 18x beam gives us a much more homogeneous beam from shallow to deep. So again, this is 6x, and I can do 10 just because I have it calculated. 10 and 18. So 6 and 18. So next, after talking about beam energy, percent depth dose, and the different parts of the beam profile curve, I want to talk a little bit about normalization. Right now I just have 100 monitor units being delivered, and then the dose kind of falls off how it naturally does based on the percent depth dose curve. But that doesn't necessarily have to be the case. I can normalize, which means that prescribe, I can tell the computer to deliver as many monitor units as needed in order to get coverage to a specific point. So I'm going to go ahead and insert a point. And I'm going to insert it at 10 centimeter deep. So CP2, calc point 2. I'm going to insert roughly right at 10 centimeter deep here. Okay, so right now you can see 65.6% is going to that calc point based on delivering 100 monitor units. Now I haven't normalized anything. I'm just telling the computer to deliver 100 monitor units from this beam. Okay, now I want to say I want to tell the computer, I don't want you to deliver 100 monitor units. I want to deliver 100 centigrade to calc point 2. And let's hit OK. And now you see what's happened. Okay? I'm normalized. 100% of the dose is going to the reference point calc point 2. So what that's done is it's pushed this 100%. This 100% of the dose corresponds to 100 centigrade. It's now forced that dose to go through the calc point. And the way that it does that is by increasing my monitor units. Right? So I was at 100 monitor units. Now I'm at 152. So the machine has been turned on for a longer period of time, which forces more radiation in through the patient, which means more dose is being deposited and being shifted deeper. That's what normalization is. I can take my calc point and I can change this. And because I'm normalized to this calc point, the dose follows along. So I'm dragging the calc point up, and you see that as I'm dragging it up, the 100% isodose line is also coming right along with the calc point. And as I'm going up, my monitor units are decreasing more and more and more. Now, I could do the opposite, and I could drag it down, and it's going to get hotter and hotter and hotter because my monitor units are increasing, because I have to keep pumping more dose in by leaving the machine on for more monitor units in order to get that dose to come deeper in the patient. Now, the curve, the percent depth dose curve, doesn't change its shape. It still maintains the exact same physical characteristic of the beam. So let me rearrange this. This is my percent depth dose curve. Now, as I change and drag this calc point up, my monitor units are decreasing. The percent depth dose curve doesn't change. The shape still stays the same because the physics of the radiation beam don't change. It still has the same fall off. The only difference is what absolute dose is associated with each part of that percent depth dose curve. So you notice that I keep getting lower and lower and lower and lower. If I go back the other way, and I go deeper, you notice that my D max keeps getting higher and higher and higher, and I'm forcing more dose to come into the patient, but the actual curve's shape doesn't change at all. The same thing is true with my profile. If I drag my profile in, let me change this. I'll drag my calc point down. The beam profile itself doesn't change. The physics of the profile don't change. The only thing that changes are the absolute dose, or in this case, I guess the relative dose, scales as my normalization changes. So that's how normalization affects. So when we do a clinical treatment plan, we're not just calculating to D max. Sometimes we may with electron treatments, but the majority of the time we're normalizing to either a point or we're normalizing to get some sort of percentage coverage of your target volume, like your PTV. So in this video, we talked about isodose lines or isodose curves. We talked about percent depth dose curves, how they change. We talked about beam profiles, the different parts of the profiles, and then we finally talked about normalization or dose normalization and how that affects the monitor units, not necessarily the physics of the beam, such as the profile or percent depth dose curves.